a few of them that are very important. All of them have like different implementation details. But in general, the idea is you have a bunch of tasks, like versions of your problem, which are essentially prompts. You have rollouts, which are just completions, potentially involving many steps of interactions, but like one sequence of stuff happening. And then you have evaluations, potentially interleaved throughout or at the end of the sequence. And what you're estimating is the advantage. The advantage here is the idea that sometimes your model will be better than others. Like these LLMs are all non-deterministic. You have temperature above 0. You have different things happen in different rolls of the dice. And this forking process of saying like, okay, this time it did better than that time, why was it different? RL is really about saying like, okay, this is the actual thing that changed, that resulted in the reward being better, the eval being better. This is the token at which I went down the good path versus the bad path. And whether you're doing PPO or GRPO, like this is the mechanism by which you get the signal of like, you have something that sometimes went better, sometimes went worse. Now you can kind of very surgically have the model learn to do more of the good stuff without changing too much overall. I think this is also kind of maybe a reason why DPO, I think people were hoping DPO would like really work well. In my view, DPO does not necessarily have this like fine-grained advantage estimate. Like it's not really clear just from like a full good completion and a full bad completion where you're really getting the signal about these complex branching processes. PPO has this, but it's also very expensive. GRPO, I think, has taken a lot of people kind of by storm in terms of like being a very nice like middle ground where it's more computationally efficient, it's like simple to implement, but also it does have this kind of forking process that comes just from sampling. There's also just too many papers. So like I think a lot of people just see a new paper every day and are like, oh, do I have to read this one? And I feel that too. Like I think it's difficult to know up front like which of these are going to be important, which of them are just going to be like noise, especially because lots of them have very sensationalist titles, like, oh, Quen doesn't work, or like, everything only works with Quen is like kind of true, but like there's also more to the story than that, and I think there's like different implementation details of like, oh, if you change the loss function like this in this experiment, then it works. And I think for most people, it is best to just like kind of set this aside and to not get too caught up in the individual details of individual experiments and individual papers, and kind of think more holistically about what is the process of reinforcement learning doing, what implementation details am I willing to kind of leave to other people to figure out and eventually come to me with like software that like has the knobs set correctly, and which pieces are actually important for solving the problems I care about. And so for a lot of people, I think the things that are going to be really interesting are things that are relating to actual software, to actual problems that they want to solve in the world, and agents, I think, are kind of the instantiation of that where this makes sense. And the thing that makes an agent is tools. The ability to interact with an environment, with a system. A lot of people here are like very excited about MCP at the conference. Like MCP is just tools. MCP is about giving your LLM the ability to like interact with stuff, to go solve problems that involve changing files, making requests, editing code, running code. And so I think these are the papers that I get excited about because they feel like there's parts of the puzzle that are not fully solved yet of like what's the right way to do all of this. Like there's still some open questions. But I think those are getting kind of refined. We're starting to see more and more, but like a lot of the code, the tools we have out in the wild to like go do this, like if you want to like go play around with RL, most code bases are like very set up for like either code and math tasks or things that are quite similar to that. This is kind of my fault. I had a snippet go viral that was like, here's how you do RL on like GSM-AK, which is like a kind of easy math data set. And then I think I've seen a lot of people like stick with this as like, oh, we're gonna RL on math. And like this is also just like math is easy to evaluate. And I think people are, like writing evals are hard. Like there's a whole track going on in parallel to this about like how to build a good eval. And so I think a lot of researchers gravitate towards things that like look like the benchmarks, that are also really easy to eval because there's like a very clear signal of like, okay, this thing is like right, this thing is wrong, good, okay, we're doing RL. But like real world tasks are messier than that. We are not going to like get great software systems just by like hill climbing on whatever question answer benchmark is popular today. What we're going to have to do is start thinking about like the actual systems at hand and the challenges that emerge when we're trying to design these rewards. And so like reward hacking is like a real thing. I think this is one of the lessons that like RL works, but also it's not like always going to work. There are things that can go wrong. And to me, reward hacking is really a message about the difficulty of building good evals. Like what you really want with an eval is for it to be easier for your model to do the task than to hack the eval. You want to build a reward signal that actually captures what you care about, where gaming it is like more difficult than not gaming it. If the model can learn to do the task directly just by doing what you want it to do in the spirit of the task, then like that is what will happen. It will flow in the path of least resistance. This is like models just want to learn, but they want to learn to do better on reward signals. And so your reward signals have to point in the direction of the thing you actually care about. Otherwise, like models will find cheats. And I think thinking about these things in combination kind of points a little bit towards a direction that I think is going to be very promising. And there's some very early signs that like this actually can work, which is like, when R1 came out, I was kind of like speculating, like what's next? What are the things that are going to unlock this sort of technique being used more generally? And people talk a lot about like generator verifier gaps, like what are the differences between like solving a problem versus checking if you have a solution? And a lot of problems like are much easier to check than solve, but this isn't like a binary thing. This is a spectrum of how difficult is it to verify a thing. But there's some kind of signs that you kind of can do evaluations on more ambiguous tasks by just breaking them down into smaller pieces and by using LLMs as subroutines in your evaluations, like LLMs that judge on steroids, or maybe you want to actually like train a specialized LLM who is really good at doing these fine-grained evaluations. I like using the term rubric as a conceptual general umbrella around reward models, reward functions, LLM as judge setups, like the criteria on which you are evaluating a thing. There's a cool paper from DeepSeek that I found very exciting when it came out a couple months ago about like how to train reward models that like generate these rubrics on the fly. There was a paper very recently that does this for creative writing and kind of found that like, yes, you actually can train reward models that will come up with nuanced, fine-grained evaluation criteria for a task on the fly given the actual problem. And this gives you something that results in a very like fine-grained score that allows you to actually do RL and like keep getting better. And I think like this is an area that I'm really excited about to keep watching, but also like multi-turn. Multi-turn is probably where we're headed. We want to do agentic search, we want to do tool calls, software, games, long horizon planning, computer use, memory. Scaling on tool calls lets you solve harder problems. And so how do we actually like do this? What's the way to go about building multi-turn agentic systems to do, and that we can use RL with? And I think the conceptual pieces here are environments are basically harnesses, rewards are basically evals, tasks are just prompts, and your policy in the RL sense hopefully should just be as simple as like an LLM API. I think the programming interface that makes sense for a lot of people is to have an API that you're writing code as if it's just a normal agent in a loop, but then this is a thing that you can use to go do RL. And so that's what I've been building over the past couple of months. I maintain a repo called Verifiers. It's finally on pip out in the world. You can just install it, but it's been a long time coming. And what it really is a toolkit of these pieces to make it so that building an agent that you can actually train with RL feels just like building an agent. So the interaction protocol here is like quite simple. Like this is the entire rollout function on the left of like what happens in the code when you're running an agent to do RL, which is that you kind of set up some initial state stuff, have a while loop for is it done yet? If it's not done, do a turn. And the thing you're passing here is a client object that's just an OpenAI compatible API. And I think this is the kind of interface that you really want if you want people to be able to go from their agent applications to something that's trainable, to something that they can use with RL. It's been a lot of fun thinking about like what are the abstractions, what are the pieces here, and so like there's things like parsers and rubrics that I think are like nice building blocks that you sometimes want to use. You can also like not use them if you don't want to, but like I've tried to make it fun and user-friendly. The other day I was like, let's train a Wordle agent. I think this was like a fun little toy problem where it's like, it's not that hard of like a game for us as humans, but like it's actually like kind of tricky to get your code to be this sort of thing where you have this like multi-turn interaction protocol that you actually can do learning with. But now it's like much easier. Like the code to do these things is like quite simple. And the reward functions can kind of be relatively simple for this sort of setup where it's like, okay, you want to reward it for like solving the thing eventually, but also like give it more rewards for doing it in less turns. And like this is a 7B model. Like works reasonably well. But one of the reasons it works, which I'll talk about in a sec, is SFT warmup as a way of kind of lowering the barrier of entry. Like the code as it is very much set up so that like your environments for RL are also just like synthetic data loops or evals where you can plug in Claude or DeepSeek or OpenAI and like test. So you don't have to like do RL to debug. You can like debug with an API in terms of seeing, is this a good eval? Is this a good reward? Once you're kind of comfortable with it, you can like use whatever API you like that you are allowed to use and make synthetic data, do some SFT on it, and now you can start doing RL, and this like helps a lot with small models. I think there's a lot of efficiency challenges that are like, I've been kind of hard at work trying to solve in terms of like having all of your computation be utilized effectively, having everything be like fully async so you don't have to worry about like batching, and that your trainer and your inference can kind of go at the same time. You can be like a little bit off policy. A lot of engineering that I'm hoping like, if you want to worry about that, great, dig into it, fork the repo, mess with things. If you don't want to, you shouldn't have to. And like, the idea here is that this should become something that more people are trying out, more people are having fun with exploring and getting a feel for it. Because if it's going to be a thing we have to worry about, if this is the future of building better agent models for your applications, like now's a good time to start. And so this stuff is set up so you can, like, on a couple GPUs, like, do a lot of interesting research. Like, the barrier of entry is like much lower now than it used to be. I have a lot of fun doing this on like a couple GPUs. We sell GPUs, by the way. Thanks, everybody. I don't think we have time for questions, but yeah.
All right, thank you so much, Will. Next up on the stage, we're gonna have Kamradt. He is the founder, one of the co-founders, and president of the ARC Prize Foundation. ARC is fantastic. They've been creating some of the highest signal evaluations as we're on our path towards AGI. They're basically helping us measure where we're going. I'm very excited to hear. I think we might even get a sneak preview today of the next version of what they're doing. So anyway, welcome to the stage, Kamradt.
Thank you. Beautiful. Today, we are going to talk about why AI benchmarking is about to get a lot more fun. But before we do, we need to go over some cool demos here. So I love the Claude Plays Pokemon demo. There's something really special about seeing this little embodied agent make its own decisions, go and play Pokemon for us from our childhood here. Now, OpenAI got in on the same game. I thought this was awesome. And then just the other day, Gemini beat Pokemon. I like seeing the little robots with AGI on top of their head. That must mean that we're already there, right? Well, if we have these agents playing Pokemon and it's already doing it and beating it, that means the game's over, right? We're all done? Well, not quite. Because with Claude Plays Pokemon, we saw that it would get stuck in the same place for 3 days. It would need interventions, it would hallucinate different actions, and not only that, there was a ton of Pokemon training data that was within the model itself. So although this is a really cool example about an agent exploring a world, there are a lot of things that we can go and improve on. So as Kyle was saying, my name is Kamradt, president of ARC Prize. We are a nonprofit with the mission to be a North Star guide towards open AGI. We were founded last year by Francois Chalet and Mike Knoop. And just last December, we were invited by OpenAI to join them on their live stream to co-announce the O3 preview results on ARC AGI. Now, there's a lot of AI benchmarking companies out there, but we take a very opinionated approach as to how we should do this. And our opinion is that the best target we should be aiming for is actually humans. And the reason why we think that is because we see that humans are the one proof point of general intelligence that we know about. And if we use humans as the target, that does two things for us, because what we do is we come up with problems that are feasible for humans, but hard for AI. Now, while we do that, that does two things. Number one is it creates a gap. And when you have that gap, you can start to measure, well, how many problems can we come up with that humans can still do, but AI can't? And then number two is it guides research. So you can quantify that class of problems and then go tell researchers, hey, there's something really interesting going on this side of the problem. There's something that we need to go check out from there. All right? So if we're going to measure artificial general intelligence based off of humans, we need to actually define, well, what is general intelligence? And there's two definitions that I love to quote. The first one was by John McCarthy, and he says that AI is the science and engineering of making machines do tasks, and this is the important part, that they have never seen beforehand and they have not prepared for beforehand. This is very important because if you've seen a class of problem beforehand, if it's already in your training data, then you're simply just repeating memorization. You're not actually learning anything new on the fly, right? The second person I like to quote on this is actually Francois himself, and he put it very eloquently within just 3 words. And he calls intelligence skill, acquisition, efficiency. And this is really beautiful here because skill acquisition, can you learn new things? And not only that, but how efficiently can you learn those new things? And humans are extremely efficient at learning these new things. So Francois proposed this definition in his 2019 paper on the measure of intelligence, but he went further than that. He didn't just define it. He actually proposed a benchmark to see, can a human or an AI, can it learn something new and then go repeat what it learned? And this is where the ArcAGI version 1 benchmark came out. So over here on the left-hand side, this is the learn the skill portion. This is what we call the training portion. And what we show you is a transformation from an input to an output grid. And then the goal for the human or the AI is to look at it and say, what's going on here? And then on the left, we actually ask you to demonstrate that skill. So it's a little mini skill you learn on the left, and we ask you to demonstrate it on the right. And if you can successfully do it, and this is what it looks like, it's just the grid editor here, then yes, you've learned what the transformation is, and you've actually applied this. And so you're showing a non-zero level of generalization as you go through this. So our benchmarks, ArcAGI2, this is the most recent one, it has over 1,000 tasks in it. And the important part here is each one of these tasks is novel and unique. And what I mean by that is the skills required for one of them, we will never ask you to apply that same skill to another task. This is very important because we're not testing whether or not you can just repeat the skill you've already learned, but we want to test all the little mini skills that you can do over time and see if you can actually demonstrate those. And if we're going to back up that humans can actually do this, well, we need to go get first-party data. So our group, as a nonprofit, we went down to San Diego and we tested over 400 people. So rented a bunch of computers, and we did this in person to have data privacy. And we made sure that every single task that was included in ArcAGI was solvable by people. So this isn't just an aim here. We're actually doing the work to go and do that. But if we think about it, there's actually quite a bit of human-like intelligence that's out of scope from what we call a single turn type of benchmark. With ArcAGI, you have all the information presented that you need right at test time. You don't need to do any exploring or anything, and it's all through single turn. So if we're gonna be measuring any human-like intelligence, and I would argue that if you are gonna measure human-like intelligence, it needs to be interactive by design. And what you need to have is you need to be able to test the ability of an agent, whether that be biological or artificial, to explore an open world, understand what goals it needs to do, and ultimately look at the rewards and go from there. So this is actually very in line with what Rich Sutton had just published within his paper, Welcome to the Era of Experience. And he argues that if we want agents that will be readily adaptable to the human world, they need to engage with the open world, they need to collect observational data, and they need to be able to take that data to build a world model and make their own rules and really understand what it is, or else you're just going to have the human ceiling, the human data ceiling going forward from here. If we're going to be able to build this, we're going to need a new type of benchmark that gets out of the single turn realm, and this is where interactive reasoning benchmarks are going to come in. Now, an interactive reasoning benchmark is going to be a benchmark where you have a controlled environment, you have defined rules, and you may have sparse rewards where an agent needs to navigate to understand what is going on in order to explore and complete the objective from here. Now, there's an open question as to, all right, if our aim is interactive reasoning benchmarks, what is the medium in which we're going to actually execute these benchmarks in? And it turns out that actually games are quite suitable for interactive reasoning benchmarks. The reason for this is because games, they're a very unique set of intersection of complex rules, defined scope, and you have large flexibility into creating these types of environments that you can then go put different artificial systems in or biological systems with it. Now, I know what you may be asking here. Wait, Greg, didn't we already do games? Didn't we do this 10 years ago? We already went through the Atari phase. Well, yes, we did, but there's actually a huge amount of issues with what was going on during that realm there. Not even just starting with all the dense rewards that come with the Atari games. There was a ton of irregular reporting, so everybody would report their own performance on these different scales, and it was tough to compare these models with it. There was no hidden test set that came. And then one of my biggest gripes with the Atari phase was that all the developers, they already knew what the Atari games were. So they were able to inject their own developer intelligence into their models themselves, and then all of a sudden the intelligence of the performance, that's getting borrowed from the developer. That's not actually getting done by the model itself from there. So if we were able to create a benchmark that overcame these shortcomings, well, then we'd be able to make a capabilities assertion about the model that beat it that we've never been able to make beforehand. And so to put it another way that's a bit more visual, we know that AI can beat one game. This is proved. AI can beat chess, AI can beat Go. We've seen this many, many, many times here. And we know that AI can beat 50 games with 50 known games with unlimited compute and unlimited training data. We've seen this happen with Agent 57 and Mu0. But the assertion that we want to make is, well, what if AI beat 100 games that the system has never seen beforehand and the developer has never actually seen beforehand either? If we were able to successfully put a test or put AI to this test, then we could make the capabilities assertion about that AI that we don't currently have in the market right now. And I'm excited to say that that's exactly what Arc is going to go build. So this is going to be our version 3 benchmark. Today is a sneak preview about what that's going to look like. And this is going to be our first interactive reasoning benchmark that is going to come from Arc. And I want to jump into 3 reasons why it's very unique here. So the first one is, much like our current benchmark, we're going to have a public training and a public evaluation set. So the reason why this is important, with our public training, call it on the order of about 40 different novel games. This will be where the developer and the AI can understand the interface and understand kind of what's going on here. But all performance reporting will happen on the private evaluation set. And this is very important because on this private evaluation set, there's no internet access allowed, so no data is getting out about this. The scores that come out of private evaluation set will have been done by an AI that has never seen these games beforehand, and neither has the developer seen them. So we can authoritatively say that this AI has generalized to these open domains here. Now, the second important point about what ArcAGI 3 is going to have is it's going to force understanding through exploration. One of my other gripes with current game benchmarks out there is you give a lot of instruction to the actual AI itself. Hey, you're in a racing game. Or, hey, you're in an FPS, go control the mouse and do all these things. We're going to drop AI and humans into this world, and they won't know what's going on until they start exploring. So even as I look at this screenshot, this is actually one of our first games. We call it Locksmith. We give all of our games a cool little name like that. As I look at this, I don't know what's going on, right? But I start to explore, and I start to understand, oh, there's certain things I need to pick up. There may be walls, there may be goals and objectives. I'm not sure what those goals and objectives are right when I first start, but that's the point. So not only are we going to ask humans to explore and make up their own rules as to understand how to do the game, but we're going to require the same thing for AI as well. And that's something that we're not currently seeing from the reasoning models that we have from there. Now, the third key point is that we're only going to require core knowledge priors only. This is something that we carry from ArcAGI 1 and 2 as well. But what this means is, you'll notice the Arc tasks, there's no language, there's no text that's being involved here. There's no symbols, and we're not asking you any trivia. So I call these other benchmarks that rely on these, sometimes we try to make the hardest problems possible. We go hire the best people in the world, and I call them PhD++ problems, right? And that's great, but AI is already superhuman. It's way smarter than me in a lot of different domains. We take the alternative approach, which is let's look at more of the floor and look at the reliability side. Let's take all the core, anything outside of core knowledge and strip those away. So core knowledge priors, the 4 of them that there are basic math, and these are things that are humans that were either born with or hardwired to gather right immediately after birth. So basic math, meaning counting up to 10, basic geometry, so understanding different shapes and topology, and then agentness, which is understanding theory of mind, that there's other types of agents out there in the world that I know that they're interacting. And then the 4th one is objectness. So as we create our benchmark, these are the 4 principles that we like to go after when we try to test the abstract and reasoning piece. Now, I was reading the recent Darkesh essay, and he actually put it really well in one of his paragraphs here. He was talking about one of the reasons why humans are great, and he says it's their ability to build up context, interrogate their own failures, and pick up small improvements and efficiencies as they practice a task. We don't yet have this type of environment that can go and test this from a benchmark perspective for AI. And this is exactly what ArcAGI is going to go build. So before we wrap it up here, I want to talk about how we're going to evaluate AI, because it's like, okay, cool, they go play the game. Well, what does it mean? How do you know if it's doing well or it's not? And we're going to bring it back to Francois' definition. So we're going to bring it back to skill acquisition efficiency. And we're going to use humans, which again is our only proof point of general intelligence. We're going to use humans as the baseline. So we're going to go and test hundreds of humans on these exact ARC tasks, and we're going to measure how long does it take them, how many actions does it take them to complete the game, and then we're going to get a human baseline, and we're going to be able to measure AI in the same exact way. So can the AI explore the environment, intuit about it, create its own goals, and complete the objectives faster than humans? Well, if it cannot, I would go as far as to assert that we do not yet have AGI. And as long as we can come up with problems that humans can still do but machines cannot, I would again assert that we do not have AGI with it. So we're going to be looking at skill acquisition efficiency as our main output metric here. Today, we're giving a sneak peek about what this looks like. This is World's Fair. Actually, next month in San Francisco, we're going to give a sandbox preview. So we're going to release 5 games. We know better than to try to wait till the end. We're going to make contact with reality. We're going to put out these 5s. We're actually going to host a mini agent competition too. So we want to see what is the best possible agent that people can do. We'll put up a little prize money. And then we're going to look forward to launching about 120 games. That's the goal by Q1 of 2026. Now, that sounds like it's not that many games, and you think it's not that many data points, but the richness of each one of these games goes really, really deep. There's multiple levels. It goes deep with each one of them. And it's quite the operational challenge to make all of these. And that's a whole nother side of the benchmarking process, which I'm happy to talk about later. If this mission resonates with you, again, ARC Prize, we are a nonprofit. One of the best ways to get involved is through making a direct tax-deductible donation from that. If anybody in the room knows any philanthropic donors, whether it be LPs or individuals, I'd love to absolutely talk to them. But then also, we're looking for adversarial testers. We want to pressure test ArcAGI 3 as best as we can. So if there's anybody who's interested in participating in the agent competition, whether it's online or offline, let me know. Happy to chat. And then also, kind of cool story, we originally started with Unity to try to make these games, and we quickly found out that Unity was way overkill for what we needed to do if you're just doing 2x2, 64x64 games here. So we're actually making a very lightweight Python engine ourselves. So if there's any game developers out there, anybody wants to get involved with this and knows Python well, we're looking for game developers and game designers as well. That is all we have today. Thank you very much. Kyle, do we have?
Yeah, I think we have time in this case for a couple of questions. If anyone wants to come up, there's microphones, 1, 2, 3 of them, maybe a couple of questions. I'm going to kick that off.
Sure, yeah. All right. Yes.
Question for you. So, and I don't know where
I can repeat, okay.
All right. It's very hard to make estimates about timelines famously, but if you had to guess, how long do you think this new version of the benchmark you're making will take before it gets saturated?
Well, the way I think about that is, well, I would say I'm counting in years. I'm not counting in decades. We'll put it that way.
Okay.
Yes.
Interesting. All right. Yeah, we'll take one at each mic. Looks like it's well distributed. So starting over here.
Sure. Hi. You mentioned efficiency as part of the requirements. And so I'm wondering for the benchmarks, if you're considering things like wattage or time or other ways of using that as one of the criteria.
Yeah, I love that question. And I would have put it in if I had more time, but I'm very opinionated about efficiency for measuring AI systems. If I could have 2 denominators for intelligence on the output, number 1 would be energy, because you know how much energy the human brain takes, and that's our proof point of general intelligence. So you can take how much calories the human brain takes. So I'd love to do energy. But the number 2 denominator is the amount of training data that you need for it, neither of which are very accessible for closed models in the current day. So we use proxies, and the proxy is the cost. But then with interactive evals like this, you get another proxy, which is action count, and how long does it take you to actually do it. We're not going to have a wall clock within these games. It's going to be turn-based. So we won't have wall clock to do it.
Awesome. All right, question 2, and then we'll do 3. Please keep them both very short.
Yeah, very quick question. Could you define more what do you mean by objectness?
Yes, that one's actually quite simple. It's just understanding that when you look out into the world, that there's a mass of things that may act together. So the crude way would be you have one pixel, but then it's surrounded by a whole bunch of other pixels, and they all move together. You understand all those pixels as one, and it kind of acting as a one body rather than individual. And really, evolutionary-wise, that's a tree over there. All this is part of the same tree, that kind of thing.
Final question, I'll keep this one super short. How do you distinguish between tasks that, in the games that you guys are developing, how do you distinguish between tasks that humans cannot do and an AGI also cannot do? Like, what is the North Star there?
It's a good question. Tasks that humans cannot do are a bit out of scope for our thesis on how we want to drive towards AGI. So I would say that's not really the aim that we're looking for on that. That's a whole different conversation around superintelligence that's for another time. Thank you.
All right, thank you everyone,
Awesome.
and let's hear it for Greg. Awesome. Okay, so our next speaker, it is my pleasure to announce bring to the stage Aakanksha Chowdhery. So while she gets up and is getting plugged in, I'll give a bit of an introduction. So she is working at Reflection AI. She's going to talk to us about using reinforcement learning for autonomous coding. This is a huge area. This is what all the big labs are doing. I'm very excited to hear more about how that how that works, how she's getting it to work. This is the perfect person to talk to us about this. Aakanksha was the first author on the Palm paper, which was, an absolute breakthrough LLM produced by Google a few years ago. She led up she was a lead researcher at Gemini early on, and now, of course, she's at Reflection AI, where she spends all her time thinking about this. So, welcome to the stage.
If the presentation works, that's the AGI complete problem, right? Okay. HDMI. I'm trying to mirror it, and that's the excitement here. Okay. You can see it, but I can't see it, so that's what I'm fixing right now. Let me solve it once more time. Good.
You good to go?
Yes.
Awesome.
Okay. Hi, everyone. I'm Aakanksha. I was at Google for more than 6 years, and I led the research for Palm, and I was a lead researcher in Gemini. These days, I'm working on pushing the frontier for autonomous coding with reinforcement learning. So just to recap the arc of how we have progressed in large language models and why autonomous coding and why now. So I think everyone here, or those of you who don't remember, in 2020 there was this breakthrough paper that came out which talked about scaling laws for large language models. And if you were to take a 30-second recap, the main thing it said was that there's a power law relationship between the test loss of large language models. So if you use more compute, more data, and put more parameters in your machine learning model, which is a transformer model, you will get more performant models. And it will not be performant just in the domain in which you are training the model. It will actually be performant, and it will generalize to many other domains. And the generalization was pretty much a feature in this particular case. So as the large language models got bigger, we saw continuous improvement across benchmarks to the point that they're starting to get saturated now. And the other interesting thing was that we saw emergent behavior where capabilities were emerging in large language models that were not present in smaller models. And this is a classic slide that I show for the work that we did in PaLM. So typically when you go about trying to solve math problems and you give the model some examples, on the left you have a math problem around tennis balls, and then you give a second problem, the model output looks wrong. But what PaLM and the subsequent set of papers showed was that if you ask the model to output its reasoning chains, which has become a very common concept now, but this is, remember, 2021, so 4 years ago. If you ask the model to show its reasoning chains, then the answer actually is correct. So basically, by getting the model to output its chain of thought or reasoning chains, the model performance improves. And this capability particularly emerged in large language models. These are all the models. So Lambda and PaLM were the state-of-the-art models about 3 years ago. And what I'm showing on x-axis is the increasing number of parameters. PaLM was scaled all the way up to 540 billion parameters. No one actually publishes the number of parameters these days, so you have to live with the graphs from 3 years ago or the open source stuff that's coming out with DeepSeek and Qwen models. But what y-axis is showing is that the solve rate on middle school math word problems was increasing with the number of parameters in the models, and it was essentially increasing mainly when you were prompting the models and asking them to show chain of thought. And this led to all kinds of prompting techniques where you ask the model to think step by step. You even go and bribe the model and such, and you ask the model nicely or not. So this was all kinds of fun stuff. And I think the thing that really stood out from this generation of models 3 years ago was that this capability was not just limited to math problems. It was basically generalizing across a whole bunch of domains, anywhere from question answering in other languages to puzzle problems to multitask natural language understanding problems. And what this led to next was that now that these models could reason, we could get them to follow instructions. So the first set of applications that became possible with these large language models were chatbot applications. So everyone remembers that ChatGPT and now Gemini and various other chatbots have become extremely popular. All of us use them all the time. But what made them really possible was that when you give instructions to the model to go do something, it's actually able to do it. And the way it learns that is actually based on reinforcement learning. And the reinforcement learning data that we're giving to the model in this particular case is essentially data based on human feedback. So you're basically saying, okay, here is a set of questions, and if I were to give it to a human and there were 2 answers, which one would the human prefer? And if you have enough of this data and you train your model, you would actually end up with better performance because you taught the model which set of responses to prefer. And this actually doesn't only work in chatbot applications, it also works in code. So on the bottom right, I'm showing that even if you were to do this for applications in code, you start to see some performance improvements. Now, of course, the question is that last year there was a whole bunch of debate as to are we hitting the wall in terms of performance of large language models, pre-training is not giving any gains, or all of these questions were on the horizon. So what is next? And one of the key questions to remember in all of this is that when you go and pre-train the models, you end up spending a lot of money on training these models. It could be tens of millions of dollars. And when you do inference on the models, it's extremely cheap. These numbers are not endorsed by any of the companies I've worked at, but these are public numbers from public sources. So going back to the main point that I want to make here is that training is extremely costly. So if you constantly try to scale up the model size, you end up in this regime of like, if it's not giving performance gains, then can we get performance gains at inference time because inference calls are so cheap? And a key idea that was extremely useful here was that if you could get the models to generate multiple responses and then do majority voting, so in the example above, I'm showing that the prompt doesn't make sense, but you've given a mathematical problem to large language model and you're asking it to generate 3 answers independently, and then you basically do some voting on top of those answers. And if 2 answers match, then that's a majority vote. Or like if in this room I were to ask a question and all of you said yes, then that is a majority vote. So similarly, in large language models, if you can get the model to like generate many, many samples and then consistently get it to get many of those answers to agree, this notion of majority voting or self-consistency had shown gains. So this kind of scaling compute at inference time was clearly one avenue to go push on. Another avenue that emerged and showed substantial value was that you could sequentially revise your previous response. So as humans, oftentimes we write the first answer, and then we go evaluate our answer, and we're like, oh, there's some mistake here, it doesn't quite match, and then you go fix it. So basically, can we get LLMs to do the same kind of revision, looking at previous set of revisions? And this was the second, so basically having longer chains of thought and getting the model to improve consistently in inference time based on that. And these kind of techniques where you could verify your correct answer, so in math or in programming where you have unit tests, showed very clear gains. So what I'm showing you here is an example from one of my colleagues' work at Stanford, which is a publicly published paper. And on the y-axis, we have pass at k, or coverage score, and on the x-axis, we have number of samples. So as you basically are doing a lot of samples on the x-axis, your accuracy is improving with open source DeepSeek model and just taking more samples. So you're getting a very high score on SWE-bench verified compared to even state-of-the-art back in end of 2024. Of course, now all of these scores have pushed up, and we are roughly somewhere around 80% already. But what we want to take away here is the fact that these lines of work, they showed that inference time compute predictably gives us gains, especially in domains where we can verify. If we know how to verify the answers, then we actually know how to translate that into intelligence. And going back to my talk title, coding is one of those domains where we do have the capability to verify, and that gives us tremendous advantage in terms of building superintelligence on top of autonomous coding. Of course, now you ask the question of what does automated verification mean here? So for inference time scaling to work, you need basically some way to say this output is correct. Now in math, this is a very simple example. If you were to give the input to solve this mathematical equation, and if you were to do the same calculation on a calculator, you can actually verify that that problem is correct, or that solution is correct. And similarly, in math, you have formal proofs, so you can actually verify that things are correct. In coding, you have unit tests. In compilers, you can actually generate the code and then use PyTorch as a verifier, PyTorch the compiler as a verifier. And in fact, in domains where you don't have this kind of verification, then there's a large gap. If you were to generate a lot of solutions and then do majority voting, you actually don't get as much gains. So what this roughly meant was that, okay, so inference time scaling would work in scenarios where I have automated verification, but that doesn't quite solve the problem for it to have real world impact. And the reason for that is shown in this graph as to typically, if you do majority voting, and this is across multiple different models on GSM-8K, which is middle school math problems and another math benchmark, if you were to sort them by correct fraction, you have to sample a lot. The correct generations could be very rare. So who has time to sample 10,000 times and then get a correct solution? You would be sitting there waiting, just finding the correct solution, unless you can actually figure out where the correct generation is. So basically scaling inference time compute with just majority voting or longer reasoning chains is great in the sense that there is some correct solution somewhere there, but it doesn't work well across the board. So what will get these models to learn to generate correctly during training? Well, in the chatbot application scenario, we saw that RL with human feedback did work. So can we apply the same principle here and get the model to generate correctly in where we can automatically verify the outputs? So our belief at Reflection is that the next frontier for scaling is reinforcement learning, and we already have proof points from some of the frontier labs as well. And as David Silver and Sutton published recently, they agree with, or rather they are the pioneers in reinforcement learning. They say that we are basically entering the era of experience, like starting from AlphaGo and AlphaZero, where you had an era of simulation. And the next set of large language model era was where you scaled up with RL using human data. But the next era from this year is really the era of experience, which will lead us to superintelligence. So reinforcement learning will be a fundamental component in building superintelligent systems, especially in areas where we have automated verification. And some proof point for why this makes sense is that in math, over several papers, this is results from 01, but over several papers, we have already seen examples that if you give the model on the right side, test time compute on the y-axis, test time compute is same as inference time scaling, and you measure accuracy on the x-axis, it should go up. But as you can repeat this process with reinforcement learning, then the training time compute going up on x-axis also improves the accuracy on y-axis for a challenging benchmark in math called AMY. Most of these benchmarks saturate within a year, as you probably have learned by now. So this benchmark is already saturated. So now that I've hopefully convinced you that reinforcement learning and scaling reinforcement learning is the next frontier, you'd be like, okay, so why is not everyone doing it? What's so challenging about it? So as I have built large language models before, a big part of building these systems ends up being that the machine learning plus system stack for these systems themselves is very challenging. So here is an example of why scaling up reinforcement learning is challenging. So if you are trying to do reinforcement learning with PPO, which is one of the algorithms used for RL with human feedback, then it moved to DPO, you have to keep 4 copies of different models. So if you imagine a really large model, and then you have to keep 4 copies, then you have to arrange them somewhere on GPUs in your large cluster. You can have some fun figuring out the exact layout, and it's a fun and interesting problem, but it's a hard problem in the sense that to make maximum utilization of these systems and arranging them in the right way, just building that system is extremely hard. And DeepSeek actually showed with DeepSeek Math that GRPO gets rid of the value model and only has 3 copies of the model, but that's still a very challenging problem. So scaling up RL is even more challenging than scaling up LLMs, because you have multiple copies of the model and you have a training loop and an inference loop. And then on the machine learning side, on the reinforcement learning side, you also suffer a lot from reward hacking if you're the model that is deciding that this is the correct answer is a neural reward model. So you, as we discussed before, in autonomous coding applications, you do have the ability to verify your output, which roughly means that you can decide this is the correct answer or not. That's how SweBench verified scores work today. You have execution feedback, you have unit tests. So all of these possibilities, of course, this is an ongoing list. All of these possibilities mean that you can design better reward functions. Okay, so this means that autonomous coding is a great domain for scaling up RL. Then the question becomes, how does this have real-world impact? So in software engineering applications, generation of code is only one part of the system. If you look at end-to-end workflows for software engineering, there is many more parts to that system. How do you scale up your system to generalize across all of those domains? So that's the problem we are trying to solve at Reflection. Our mission is that we would like to build some superintelligence, and we are starting with autonomous coding as the root node problem for this mission. And we have a team of about 35 pioneers who have pioneered various legendary works in LLMs and reinforcement learning. So if you're excited about this mission, you can reach out to one of us, or my email is my last name at reflection.ai, and we would love to work with you. And with that, I can take questions.
All right, same protocol as last time. If you have a question, please come up to one of these 3 microphones we have distributed throughout. We can probably take 1 or 2 questions, so if you want to ask something, feel free. I guess I'll do the first one while people are coming up. So I'm curious, it seems like the foundation models are trying to build one model and deploy it across everything. Do you have an opinion with the work you're doing right now if you think that's the right approach, or if you think there'll be more specialization on different languages or even like individual code bases, or do you feel like the best approach is just to have like one model that's trained across the greatest diversity of tasks possible?
I think I will answer your question in terms of building coding agents does require multiple capabilities, and how you get there, you will definitely need multiple LLM calls. And then whether that's one model or multiple models, I think that's the secret sauce right now for most people.
Fair enough. All right, please.
Hi, I'm wondering in the slide with the chart of era of simulation, era of something, and era of experience, they had put in AlphaGo and the previous one where also they played StarCraft or something. They all used MCDS, which, I mean, maybe it's my unfamiliarity with them, but it's also data simulation.
Mm-hmm.
So we're using synthetic data for era of experience as well. So why is that called simulation, and why is what we're doing right now not called simulation? What's the sort of overlap between simulation experience? How do you think about that?
I can ask Dave that question, but going back to the point, I think the better way to answer that question is roughly what Greg covered in the last talk, where his comment was that, so in gaming, you can envision what scenarios might happen next, and you're basically using that to build your reinforcement learning. So you're doing rollouts, and you're basically building based on that. In real world, in most scenarios, you have an imperfect rollout. So you don't have full knowledge of how the system might work. Simulation is possible in certain domains where you do build a world model, which is closer to robotics and all the work that's happening in the physical AI space, right? But in the real world applications, which is what we're targeting, you will have imperfect things. So you have to actually experience the real world, and you have to collect some data, and that data is not going to be in any way complete, nor will it completely search the exponential search space that could exist.
Awesome. Thank you so much, Aakanksha. We'll have to stop it there. But I assume, will you be around afterwards to answer questions? Awesome. If you have more questions, please do. Next, we're going to welcome to the stage Ryan Marten. So Ryan is one of the founding engineers at Bespoke Labs. Sounds like he's got a friend. Anyway, we are very excited. So Ryan's going to be talking about a project that he worked on, that they worked on, building a reasoning model. It's called OpenThinker, that actually is able to outperform the distilled versions of R1. So he's going to talk through what they built there and yeah, like what we can learn from it. So welcome.
Thank you. Thank you. So yeah, I'm Ryan. I'm a founding engineer at Bespoke Labs, and today I'm going to talk to you about OpenThoughts, which is our project to create the best open source reasoning data sets. And I'll be switching tack a little bit from our earlier discussions on reasoning and RL and focus on the reasoning part, and you'll see why. So just so we're on the same page, we've talked a lot about reasoning, but what's actually going on here? So I like this graph from Jason, which shows this incredible performance that's happened in the last several months, where models are getting much, much, much better on certain benchmarks. And if you look at that, this is reasoning, this is test time scaling. I think everyone here is quite familiar with this, and it seems that certain tasks like AMY, which are competitive math problems, really respond to models when they're able to think step by step and do these long chain of thoughts. So let's go back to DeepSeek R1. Now, DeepSeek R1 was really impressive for a lot of people for a lot of reasons, and RL was a big part of that. But I was also particularly interested because DeepSeek R1, at the end of the day, is an SFT model. So the final weights that they've released are actually from DeepSeek v3 base, which is fine-tuned on 800K SFT examples, 600K of which are reasoning. Of course, you can see here that RL was a big part of it, and RL was used heavily to create that model which generated this data. But at the end, it was SFT and a little bit of RL for alignment. So this was really interesting and surprising. And the other thing that was really interesting and surprising to us was these small reasoning models that DeepSeek released, which were incredibly strong. And this, for us, was a huge motivation to try to do this ourselves. And why is that interesting? Because if we go back to here, no additional detail was really given on these data sets here. So if you want to create strong reasoning models, we now sort of have a training recipe, but we don't have the data recipe. That's the missing link. Okay, I want to also include a slide here on why is it interesting to train your own reasoning models. So I'm partially taking this from Amir's talk yesterday on open source and enterprise, which I really liked. But there's these main points: performance, privacy, speed and cost, and then ownership and destiny. I think using reasoning is a great tool to solve a problem. And you shouldn't limit yourself in your toolbox if you're trying to solve a specific domain task. So as we talked about before, RL is a great tool in this toolbox to tackle reasoning tasks, but we're going to see here that SFT is, as Nathan put this morning, extremely easy and extremely effective. Okay, great. Now, the missing link. How do we actually solve for this reasoning data recipe? There's all these questions that we had when we started. How much data do you really need? What data curation steps are necessary? What are the optimal choices for each step in that data creation pipeline? And then how do you even go about figuring all this out? And this is the meat of the OpenThoughts project. So today we're excited to announce OpenThoughts 3, which is hot off the presses, just came out 2 hours ago, which is our latest and greatest version of our reasoning data sets. And yeah. Thank you. And now this is the state-of-the-art reasoning dataset recipe. So you can see here, these graphs are showing accuracy on 3 of these reasoning benchmarks: AMY, which is competitive math, Live Code Bench, which is competitive code, and GPQA Diamond, which is our science questions. On the y-axis, you see accuracy is going up. On the x-axis, you see the data scale is going up. So we heard before that scaling is difficult, particularly difficult with RL. The good news is for SFT, scaling is quite easier. You can see here we compare to other open reasoning data sets. So Nematron Nano, NVIDIA released this great model, Nematron Nano. It's an AP model, and they also released the data set to train on it. So we compared directly by training on the same base model between our data set, which is our data set recipe, and the Nematron Nano data, which is the NVIDIA recipe. And you can see here there's a significant gap. So we shifted this scaling curve upwards. Great, so this is the state-of-the-art 7B open data reasoning model. You can see we have measured across the domains of interest, so science, code, and math, and then a couple held out benchmarks. So our original goal was to reproduce, to find the missing link for the DeepSeek distill models. And you can see here we've crushed that goal. So we're significantly outperforming the DeepSeek R1 Qwen 7B model, which we started off trying to reproduce. And then compared to the Nematron Nano model, which is trained on a different base model, we are also outperforming on some benchmarks and similarly competitive on some others. So okay, let's actually talk about how we achieve this. This is the interesting part for you. So if we go back to the scaling graph, you can see, once again, on the x-axis, we're scaling data set size. So this is a huge method to increase accuracy. And the thing here is it gets more and more expensive, exponentially more expensive as you keep going. And then vertically, you can see that we've shifted the scaling curve up. So this is what I was talking about before. This is the improving the data set recipe. So given a fixed data set recipe, you can always scale it larger and you can always have higher performance. But if you want to push your performance to the absolute maximum, the real question is, how do I create the best data set? And therefore, what is the best recipe for the data set? Okay, so enough teasing here. Let's go into the meat of it. So this is how we approach this problem. We broke down the dataset pipeline into sourcing questions, mixing different sources of questions, filtering those questions, filtering out the highest quality questions, generating answers with a teacher model, so that's distillation, and then filtering out bad answers. And lastly, at the end of this entire experimentation, we looked at what are the best teacher models, which teacher model should we select. So through this entire pipeline, we've come down to this final dataset recipe. Now, this was a ton of work. This is a screenshot of our Hugging Face page. So you can see created over 5,000 data sets and almost 3,000 models. For this project, it was only around 1,000 experiments, but just to give you an idea of how rigorously we looked at the different decisions in each of these steps of the pipeline. And also, I think this is interesting because it peels back the curtain a little bit on maybe what the frontier labs are doing, finding signal at the smallest scale possible and trying out as many things as possible and empirically choosing the best and then scaling. And often sometimes when you scale, you see, okay, what was the best at the small scale doesn't actually work. But if you're lucky and you've done good science, then your YOLO run will be the best possible, right? Okay, so these are the key learnings that we had from our dataset recipe, and this is what you can take away. So the first thing is that, pretty surprising, sampling multiple answers, so multiple reasoning traces per question in your dataset works really, really well. The performance does not go down at a fixed scale. If you take a fixed scale of questions, say 30K questions, or 30K examples, and of those, if you take just 30K questions and you only sample once per question, that performs pretty similarly to if you took 1/16, so 30K over 16, and then for each you sampled 16 times, which is quite cool. So this allows you, this is really cool because this allows you to scale by 16x, which is more than an order of magnitude. And if you remember the graph from before, that corresponds to a pretty large increase in accuracy. But the other surprising thing that we found was that a better model in terms of its own performance on evaluation benchmarks does not necessarily mean it's a better teacher model. I think a good way to think about this is a brilliant researcher who's maybe a terrible lecturer, right? We found specifically Quen32b was a stronger teacher model than DeepSeek R1. So we switched to that in our recipe, even though previously everyone has been using R1. We also found that the sources of data that had synthetic questions were actually quite good. Some of the top sources that we selected were entirely synthetic, and better than sources, say, that scraped from forums or had humans manually write things. And this is also really good news because synthetic question generation is scalable. So once again, we go back to the x-axis and we can push even further, which is accuracy boost. So question filtering also works well. Here we filtered questions by asking a language model, how difficult is this question? And then taking only the hardest questions. We also had a language model try to answer that question and looked at the length of that answer. So these are sort of proxies for the same thing. You can imagine that if a problem is a lot harder, then a language model will think more and it will produce more text, so its answer will be longer. And these things worked better than embeddings-based approaches or fast text classifiers, which is interesting as so much that those approaches were typical for pre-training. So it seems that the filtering for data and post-training is quite different than pre-training. Okay, some things that didn't work that were also quite interesting. Through our experiments, you saw that choosing a smaller number of high-quality sources was much better than trying to optimize for diversity by going for a larger number of sources. That's very counterintuitive, right? You'd think, okay, I'm always going to go for higher diversity, but this is actually not what we saw. The last thing it was interesting is that people talk a lot about verification, which is obviously very important for RL. And we actually see for SFT and distillation, it didn't seem that filtering based off of the answer or verifying the answer really helped at all. This is quite surprising. And I think there's some good research in the literature about maybe why this is, because if you have the hardest problem, it might be still helpful, even if you have an incorrect answer to that hardest problem, keeping it in and seeing how the teacher model attempts. It's not just the final output that matters. Okay, great. Okay, so those are all like the amazing learnings that we had for OpenThoughts 3, which super excited to share. But now you're probably thinking, okay, they've done 1,000 experiments. I don't want to do 1,000 experiments. I still want to create reasoning models. How do I adapt this if I want to create specialized reasoning models? So I guess the first thing I would say is be aware that based off of your domain, these exact choices might be a little bit different. I would suggest, okay, start with our recipe and then iterate on it. If you have capacity and compute, try a couple different choices for each step in the pipeline. And I think a good example of this is we studied each step in the pipeline differently by domain. So we studied it distinctly for code, science, and math. And we saw, for example, in the question filtering, which I talked about before, using difficulty labels worked well for code questions, but for math and science, it was a response length. And if you think about that for a second, it makes sense because the response length for coding questions are very different, right? For AMY math, it's literally just a number between 0 and 1,000. So the answer is not considering a large portion of the length. But you can imagine there's very simple coding questions in which the answer is still a lot of lines of code. So yeah, this is one thing to be aware of. The other thing, which I talked about previously, is synthetic question generation. Because it works so well, and if your specialized domain, if you don't have a lot of data for your particular problem, then go ahead, transform that existing data into questions, expand it, throw those as in-context examples, and generate more data. So yeah, we built an open source library for this. It's called Curator, and you can try that out. And then lastly, I feel like everyone says this, but it can't be said enough. Like, the evaluation is paramount. If you don't know how well your models are doing or improving, then you cannot make good principled decisions about your data set recipe. We spent a lot of time on this. We also have this open source library on GitHub called Evalchemy, which takes care of this and also takes care of the sharding and parallelism. And the key thing here is for very small evaluation sets, if you only have a handful of questions, you should run your model on those evaluation sets many times in average. So going back again to AMY competitive math questions, there's only 30 per year. So for our evaluations, we gave the model those 30 questions 10 times, and then we averaged to get the final signal to determine which data strategies were working better than others, because otherwise there's too much noise. Okay, this is also very, very interesting and surprising, and promising for you if you're specializing. It seems that you can actually surpass the teacher in some domains with distillation. This is super cool. Usually you think about only RL can push the frontier. Distillation is just about catching up to the teacher, but no, that's not the case. So we have an example, it's in our paper, where we looked at the legal reasoning domain. So the problem of classifying Supreme Court decisions. And what we did is we took 2K unique questions, we sampled 5 answers per question, and then we did do verification here, which did matter. So we threw away any questions, any answers that were incorrect. And when you fine-tune the 7B model, it surpasses R1, which is a very strong reasoning model and also a very huge reasoning model. So this is very exciting, and there's a lot more research and also application to be done here. Okay, cool. So everything's open. It's OpenThoughts, and OpenThoughts means open. Go out and build. We have all of our, we've got our detailed paper. It's just out this morning. We've got the weights data set. We have a ton of repos for code, for data generation, for evaluation, and synthetic data. So check those out. This is the team. It was a huge group of people, a lot of work over many months. I think we're all very proud of what we did, but there's lots of people to recognize here. If you scan that QR code, it goes to the tweet, and everything about the OpenThoughts project is linked in from there. Yeah, thank you.
All right. Thank you so much, Ryan. That was fascinating. Looks like we have at least one question lined up. Again, we have time for maybe a couple of questions. So if you have questions, please line up and we'll do it. Actually, before we get to those questions, I will say as people are leaving, we are going to be back here at 2 o'clock. We've got an excellent afternoon planned on this track. We've got Nathan Lambert. We've got Christian Szegedy, who's the co-founder of X. And it's going to be a really great track at 2 o'clock back in this room. Also, one more thing, if you do have questions for any of the speakers from this morning, hopefully they're going to be able to stick around. Don't let them go to lunch. They're sitting up here at the front, so swarm them as soon as we're done. But for now, let's get a couple of questions go ahead. Yes, over there.
Thank you, great talk. So 2 questions. One is, if you're just using SFT on this data, what's the difference between this and regular SFT?
This is just regular SFT.
Oh.
Yeah.
Oh, okay. So then how is regular SFT able to make the models like think longer? Because I thought for the reasoning models, they have like a thinking block and they think for hours and minutes and
exactly.
So how does SFT make it think for hours?
So you're doing supervised fine tuning on the questions, and the answers also contain the thinking. So the model learns to use its context window and produce these long thinking traces. So it can do this. People call SFT imitation. But it can learn this format in the same way. Yeah.
Thanks.
All right, we'll take one from this side.
Great presentation, Ryan. One question: why do you think a smaller model like Qwen 32B was a better teacher than DeepSeek R1? What was your insight in figuring out that like a good professor makes a bad lecturer?
Yeah, that's a great question. I think this is something we need to investigate more. But you can see that. When you look at charts of the length of reasoning traces, you can see the distributions are different. So it might be the case that you're using more of your context window, using more tokens, more steps. It also might be the case that you just have a better formatted response, better output. This is like another great open research question. Interesting, I'll also say on this point, we also tried Claude as a teacher, which is like as a good, strong model, and it was just a terrible teacher. So there's it's interesting what actually creates a good teacher. Yeah.
All right, we'll take one more very brief question from this side, and then those of you still waiting on questions after we have closed this up, swarm in.
So great talk, Ryan. We're doing similar kind of thing, but I just had a question. Do you guys have any like pattern map as to in the reasoning chain of thought, when things don't work, at what level, in the eval, do you find out that things are not working or it's not reasoning correctly? Is there a pattern map or something that you have in your open source graph?
Sorry, I didn't catch that. Is there a...
So if there are 5 steps of reasoning to reach a final conclusion, at what step does the reasoning go awry?
Yeah, this is a great question. We don't do this fine-grained analysis, but there is a ton in the literature about this, where, there's a sort of critical step where it gets things wrong. We did like the simplest thing possible, right? You could also go in and try to do more complicated things. At evaluation time, where you're doing interventions to maybe detect steps that have gone awry and change. Or you can do this when you're creating the data set. So you could potentially rewrite things. But everything that we tried in terms of like messing with the reasoning trace, it wasn't helpful. So I think there's still more to explore there. This is really just the start of everything in reasoning.
Awesome. Thank you everyone for your questions. And one more time, thank you to Ryan for everything you shared. All right, and again, we'll be back in this room at 2 o'clock sharp. We have 3 more presentations. Looking forward to seeing you then.
So we need what? This just graphics only, that one?
Backup graphics tool. Trying to set this up for the overflow? No. Or John on the phone? No. Oh, no. Is that all you wanted? Was just full graphics? I think he's watching it on the screen. No, this session goes into first screen. Yeah. I'm saying on the screen now they want to see this. What's up? BU backup. Backup. This one right here, the graphics tools from the stage.
Testing, testing. What the fuck? Testing, testing.
All right. Hey, everyone. Glad you're all here. This is the Reasoning and Reinforcement Learning track on the afternoon of the last day of the AI Engineer World's Fair. Glad you're all here. Glad you're sharing it with us. To let you know what the schedule is going to be, so I'm going to be talking right now. I'll give myself an introduction in a moment. Directly after this, we're going to have Nathan Lambert from AI2. He'll be coming up. Very excited to see that. And then Chris Szegedy, formerly of XAI, one of the co-founders there, will be speaking last. So hopefully you're all able to stay for those sessions as well. I think they'll be excellent. To introduce myself, my name is Kyle Corbitt. I am one of the co-founders of a company called OpenPipe. What we do is we do reinforcement learning to make agents more reliable. We work with large companies, usually Fortune 500s, things like that, and help them make their agents more reliable so they can deploy them in production. If that describes any of you and you want to talk to me after, happy to chat later. But today what I'm going to talk about is a very specific case study that we did. This case study, I'm going to talk about lessons learned very concretely, what did and didn't work, how we were able to build an agent that worked well with reinforcement learning. All of this, everything that I'm talking about in this presentation, this is an open source code base that we built. We wanted to share these learnings, and I'll share that link with you at the end as well for those of you who want to replicate what we did. So what is the project we're going to be talking about? It's a project called ART-E. It is a natural language assistant that helps you answer questions from your email inbox. So I'll give you an example of what we're talking about here. Let's say you want to ask, in this case, our example question is, when is Sherry's move to Portland targeted for? So you would ask this question to the assistant. It then goes and it searches your inbox. It's got several tools. So it has like a search tool, it has a read email tool, and then it can actually answer the final question. You can kind of see, if you look here, what's going on behind the scenes. This is important so you get a sense of kind of how this agent works. And as we're talking through how we built it, how we made it work, hopefully that helps make the conversation very grounded in a specific task. So anyway, you see the agent. It's searching for certain keywords, it gets those messages back, it's then reading one of them and answering the question. That's what it does. Okay, so question, once we've decided this is kind of the task we're trying to solve, why would you use reinforcement learning for this specifically? And the answer is, to start with, you shouldn't. In fact, to start off with, we did not. So the first version of this agent, once we decided we wanted to build this, we didn't use any reinforcement learning at all. We purely built this on prompted models. And this is the first lesson from this talk that I want to share is I would generally always recommend starting with getting the best performance you can with a prompted model before going to any training, including reinforcement learning. There's a few different reasons to do that, 3 specifically. The first one is just like working out the bugs in your environment, right? Maybe your tools aren't implemented properly, maybe they don't have access to the data you think they do. We find this happens a lot, and it's a lot less frustrating to debug that, separately from debugging your training loop. So you want to make sure that you can get at least some kind of performance before you start training. And then second of all, you may find as you're trying to improve the performance on using these prompted models that you can get it working really well, and that's great. So that means you don't need to train anything, and that saves you a lot of time. There's a third reason as well that I'll share, which is basically once you've gone to that effort, you've done your best to get the best quality prompted baselines you possibly can. Then if you find that those baselines are not able to get you where you need to go, and you're able to surpass them with reinforcement learning, it feels great. You get to gloat and be like, yes, I was able to beat the frontier models on my task. I highly recommend it. Feels good. You can post on X about it. There's nice graphs and stuff. So this is what it looks like when everything goes right. So this is an example of a training run for this ART-E model that I'm going to be talking about. You can see that there's these lines for each of the prompted model baselines that we've got. So we've got 03, 04 mini, and then Gemini and 4.1. And you can see those ones, they have certain level of performance. And then you can see this sort of moving line that's going on. This is the model that we trained. And you can see it actually starts out significantly worse than these other models from the start. That's because we started from a Qwen 2.5, the 14 billion parameter one. It's a relatively small model, relatively weak model, and so it was doing much worse than these initially. But you can see as training progresses, initially at the beginning, it's sort of maybe it's learning the right way to do tool calls. There's a very sharp bump as it figures out the basic stuff, and then a more gradual climb until eventually it's able to significantly outperform any of the prompted models on this task. And this is sort of what you're, in the ideal case, when everything works, this is what you're looking for. This is what you're hoping to achieve. This is another view, actually, of that same data we were just looking at. I wanted to highlight it in this way because it's important to realize, so on the last graph, it looked like the lines sort of asymptote out pretty close together. That's because they're getting near 100%. But the last, you can see, for example, with our best prompted model here, O3, it's 90% accuracy. And with our RL model, we're able to get up to 96%. And so one way to think about that is like 60% of the errors that O3 was making are actually solved with our model, which is quite a large, we find that that's actually can be very, very important for the user experience of someone using one of these. If you're getting, just half as many errors, that can make the product much stronger. So this is where we got to on accuracy. There's a couple other metrics that we find are often very, very important, and the trade-off between these is very task dependent, but they matter in many cases. Cost obviously is a big one. So for this email agentic harness that we had, we benchmarked the cost on O3, O4 Mini, and our model. So if you wanted to do like 1,000 searches using O3, that's going to cost $55, which is a lot. I think for most use cases that probably would be cost prohibitive just from a unit economics point of view. On O4 Mini, we're down to $8, but that's still quite expensive. And then we drop another order of magnitude by moving to this smaller Qwen 2.5 14B. Again, this is just driven by it being a much smaller model, so it's much cheaper to run, but we're still able to get very good performance because we've specialized it on our task. Beyond cost and the accuracy, the third metric that often comes up is latency, particularly if you're doing, certainly anything with voice, but if there's any real-time human interaction with the task, latency is going to matter a lot. And we were able to find on this task, we were able to get significantly better latency. There's a number of different ways, which I'll go into in more detail later, that we were able to achieve this. One was just, again, moving to a smaller model helps. There's just less loading from memory, less matrix multiplies. It's just you're able to get tokens out faster. We were also able to train this model to have fewer turns going back and forth with the database, with the actual email, the list of emails. We were able to train it to be more efficient with its queries. And I'll go into that in a moment, and so that leads to lower latency. There's actually a third thing which we didn't apply here, but can help a lot with these smaller things, which is called speculative decoding. That's something you can do on large or small models. It generally works better on smaller task-specific models because you get higher acceptance rates on your speculator. But basically, there's lots of reasons why smaller models work better. Okay, so then the next question, for those of you who haven't done this yet, is like, okay, what is the effort required to do this to actually achieve these results? If you'd asked me this question a year ago, I would say, hey, you should really only be doing this if you're this big company and willing to put months of work into a project. I think that's changing. I honestly do. In this case, so this training run, it cost us about $80 in GPU time. It did take about a week of engineering time to build this, and caveat that was with an engineer who is familiar with this domain and had quite a lot of experience with machine learning and RL. But I actually expect as we figure out the right patterns here collectively as an industry, this will keep dropping, and I expect that the sort of payback period to get a return on investment from these specialized models is actually going to continue falling as well. Part of the reason I wanted to give this talk is to sort of distribute that the knowledge we learned and hopefully move faster towards that world where this is just sort of like a thing everyone knows how to do and is very easy and very fast. So that's what we'll be talking about for the rest of the time is some more of the lessons we learned. Okay, so when you are using RL to train an agent, or really using RL for anything else, I find that consistently with different problems we look at, there are sort of two hard problems that come up every single time, all right? And the two hard problems are, first of all, figuring out a realistic environment, right? So if you're training an agent, you need to be training it with realistic data, with realistic inputs and outputs, tools available, everything like that, to how it's going to be used in production. Because if you don't, then it's going to be optimizing for the wrong thing, and you won't get the results you want when you deploy it. And then the second thing, which sometimes is hard, sometimes isn't, this one is a little bit task dependent, is getting the right reward function. So reward function, that just means you have to be able to know when your agent's gone through, and say in this case, give it an answer to my email, you have to have some way of knowing, did it do a good job or a bad job? All right, that's the reward function. It decides, it's how you decide if it's good or it's bad. Depending on the domain, sometimes that's really easy. We have, I don't know if Nathan's here, he's going to be talking next, but he and his team put together this thing called RLVR, which in some verifiable domains, it's actually very easy to do a reward. Oftentimes, not all domains are like that. Oftentimes, it is kind of hard, and so it's somewhat task dependent. I'm going to go through how we solve these problems specifically with RE. Okay, first one, realistic environment. So for our RE task, what is the environment we need? What is the environment this agent's going to be operating in? Well, it needs these tools available. It needs to be able to go and query an email inbox. It needs to be able to like get emails back and that look realistic. These emails, you know, the inbox should be large because that's what most email inboxes are like. The emails in it should be diverse, and they have to look kind of like real emails. So this could be kind of hard because you can't just go ask like 1,000 people to, you know, give you their personal emails to train on. Luckily, in this case, we were able to solve this with the help of a company that has contributed a lot to just the open data ecosystem generally. It's like quite an iconic company. Perhaps I would call it a historic company. I'm, of course, talking about Enron. I'm hearing some laughter. So anyway, Enron was they were a financialized energy company in the 90s and 2000s, committed massive fraud, ended up getting shut down by the Department of Justice. As part of this process, the court cases they were going through, a dump of like 500,000 of their emails was released to the public as part of the discovery process. So that's great for things like this, and that's what we used as our environment for the email inboxes. All right, so now we've got realistic email inboxes with tens of thousands of emails that are real emails back and forth. Now we have to design our reward function. So as our agent is going, and as our agent is, we're asking it questions, and then it's giving us answers, we have to know, is the answer correct or not, so we can reward it when it gets the answer right, and it can learn to do that better. There's different ways, and this part is very task dependent. The way that we went about it in this case was we basically turned it into more of a verifiable problem. And the way we did that was we actually took our email inbox, we sort of inverted the problem. We grabbed batches of 20 emails at a time from the inbox and gave them to Gemini 2.5 Pro and said, hey, given this set of emails, give us a few questions that a user might realistically ask that the answers are found in this email, right? And so Gemini generated the questions, it generated the answers, and then of course the source emails that came from. And there were some extra steps on top of that. A lot of the questions it came up with looked a little bit unrealistic. We had a separate filtering step where we're like, okay, let's find the subset of these that actually look like questions that I would maybe ask. And we ended up with a list of a few thousand questions along with their verified answers. And so at this point, it becomes much more of a sort of verified thing. The reward function becomes much easier because we know what the correct answer should be. And so the way we can tell if our agent did a good job is we give our agent the question, we let it go and search the email inbox and try and find the right emails and everything, and eventually it comes back with an answer. And then we can just use an LLM as judge, a very simple one, and say like, hey, here's the question, here's the golden answer that we believe is right, here's the answer we got from our model, is it right or not? We did have to do a little bit of iteration there, making sure that the judge was well calibrated on like what counts as correct or not. But by and large, this worked pretty well and was able to make this more of a verified task. So that's how we solved the reward function problem, was by having that, turning this into something where we had more of a golden data set. Okay, so once you've solved those problems, once you have your environment, once you have your reward function defined, then basically you just kind of have to run a loop over and over and over again where you have your agent go through and it tries to solve the problem, and then you figure out if it's good or it's bad, and then you just reward if it's good and punish if it's bad, and that's it. You do this over and over and over again, and then hopefully, if you've got everything set up right, it learns what good looks like, it learns what bad looks like, and it starts doing it right. And then again, this is the curve we saw earlier, where you can see it starts getting better over time. Okay, a few other interesting learnings from this project. One thing is we found that there's actually, you can throw a lot of stuff into your reward function beyond just the primary thing you're trying to solve for. And so we actually ended up, there were sort of 8 different little things that we gave extra credit for. I'm going to share 2 of them here. So the first one here is we were trying to have it optimized for the number of turns, how many times back and forth, how many times it had to query the email inbox before it came up with the right answer, right? So because the most important thing, of course, is getting the answer right, but between 2 answers that both get it right, we would rather it took fewer turns back and forth because that's fewer tokens, that's lower latency, lower costs. It's just like a more efficient agent. So you can see here on this first graph that early on, while it was getting its feet wet and figuring out what worked, it ended up spiking up to over 6 turns on average. So it would go back and forth a bunch of times with the email inbox and try and find the right thing. But then once it was able to figure out how to use the tools efficiently, figure out like, the right way to construct keywords and find the right email, it was able to get very efficient and actually better than any of our prompted models on this metric of using fewer returns. And again, this was just because we gave it a little bit of extra. It was a very small amount relative to the reward for getting it right, but a little bit of extra credit on using fewer returns, and it was able to use that to optimize against that. Another extra reward function we gave it is to try and discourage it from hallucinating answers. So obviously, the best thing is to get the right answer. If you can't find the right answer, it's much better to say, hey, I don't know, than to make up an answer in a situation like this. So we basically penalized it. If the reward model said, hey, you got the answer wrong, but it had tried to give an answer, that was like a much lower reward than if it just said, hey, I don't know, I can't solve this problem. And as you can see, that worked quite well compared to any of the prompted models, including O3. We ended up with a significantly lower hallucination rate because that was part of our reward function. Again, these are things that are just sort of like extra credit, but we found that like you can throw in a bunch of these and it can jointly optimize all of them at the same time, which is super powerful. Okay. I want to talk a little bit about reward hacking. It's something that comes up a lot when you're trying to do this, and it's kind of a fun thing to talk about. This is an iconic video some of you might have seen. This was released by OpenAI almost a decade ago at this point. They were trying to, they had this environment where you were trying to get this boat to complete a race. And instead of learning to complete the race, it learned that, oh, if I just go in this like little circle that's not even part of the racetrack, I can like just get a bunch of points. And so it just started doing that over and over and over again instead of like actually following. This is something that comes up a lot if you're doing reinforcement learning, and it's basically just the difference between what you actually want the model to do and what you can measure, like what you're actually rewarding it for. And if you almost always, if you let one of these run long enough, it will figure out some way to exploit your measure, and it will figure out some way to get a really high reward without actually solving the problem. And you need to just watch for that. So I'm going to give a couple examples here. This is a graph from another project, actually, not this one. So an engineer on our team was working on this game called NYT Connections. Some of you might know. You get 16 words, and you have to put them in like 4 groups of 4. It's quite a challenging game, especially for these language models, because it requires a lot of world knowledge and like lateral thinking. Anyway, so they were trying to train this model to do it, and it wasn't figuring out, and then boom, you can see here around step 40, it just like takes off, and it's like, okay, we figured out how to solve this. And this engineer, I'm gonna call out. Where's Anki on our team? He's here at the conference. Yeah, he's great. You should talk to him after. But he was like, hey, we solved it. Like we got NYT Connections, and it's like, okay, the graph looks good. Let's look at what it's actually doing. What it was actually doing is it had figured out there was a bug in how we wrote the verification. And if it just put every single word in every single category, it was able to get a perfect score. Because we weren't verifying that they were, in fact, only 4 words in each category. So this is another example. This is a fun one. So I was training a model to produce really good titles for Hacker News, titles that would get a thing upvoted. So I had this reward model I'd trained on like existing Hacker News articles and how many upvotes they got, and I was trying to train this model to produce new titles. And it was working really well for a while. You can see, and sort of subjectively as well, I looked at a bunch of these titles generated, and for these first like 1,000 steps or so, it was actually learning things that I was like, okay, as someone who spends way too much time on Hacker News, yeah, that does look like a good title. You're doing a good job. And then you can see around step 1200 here, it just like jumps a bunch, right? And it's like, okay, it clearly figured something out. I don't know what it figured out, but we should look at that. And so it turns out what the model had figured out was that it could just completely ignore the content of the post and generate the same title for every single one of them, and that would like maximize its score. So it generated this title, Google lays off 80% of workforce. Literally every single article, this was what it labeled it as, and the reward model was like, yes, that is going to get upvoted on Hacker News for sure, which it probably would, to be fair. So anyway, the way we solved this, what we found is that it's really important to watch out for this. Solving it typically involves modifying in some way your reward function to penalize things like that. So in this second example I talked about, it was actually quite an easy fix once we identified it, which was just add an extra LMS judge that looked at the title, looked at the content, and said, hey, is there anything in the title that's not supported by the content? And we added that on, and it actually worked great. The important thing here is you want to be looking at your rollouts, not just blindly trusting the reward function, figuring out what's actually happening. Anyway, so that's it. I'm almost out of time, so I'm going to stop. A couple of QR codes for you. Everything in this presentation, and there's a much longer write-up I have of this whole project. It includes the code, it includes the artifacts, data sets along the way. You can check that out there. One more thing is we have a Discord that's open. We have an open source project for training reinforcement learning models. We have a Discord you can go to if you're interested in this kind of thing. We're all in there. We answer questions. There's lots of people from the community trying to do these things. So if you're interested in building things with this, feel free to join it. And yeah, happy to chat there. And yes, thank you, everyone. Appreciate your time. All right, and since I am also, in my separate hat, the moderator for this track, it is my great pleasure to welcome to the stage Nathan Lambert. Everyone give a round of applause. Nathan, for those of you, I'm sure many of these people know who Nathan is. He's probably the strongest voice in sort of the open ecosystem talking about post-training generally and also reinforcement learning. He's got a great newsletter he does, as well as he puts that out as a podcast and lots of content on X. But anyway, very excited to see what you'll say. Oh, and also runs a bunch of projects at AI2. They build probably the best fully open models. So anyway, yeah, let's hear it for Nathan.
Okay, thanks for the intro, fellow Seattleite, and I'm sure we'll talk more. I really came to this thinking about trying to reflect on 6 months into this like reinforcement learning with verifiable rewards, post-01, post-DeepSeek. And I think that a lot of this stuff is somewhat boring because everybody has a reasoning model. We all know the basics of you can scale RL at training time and the numbers will go up, and that's deeply correlated with being able to then do this inference time scaling. But really in AI right now, there's a lot of people who are up to speed, but the crucial question is like, where are things going to go and how do you skate where the puck is going? So a lot of this talk is really me trying to process is like, where is this going besides getting high benchmark scores with using 10,000 tokens per answer? And like, what do we need to do to actually train these models? And what are the things that OpenAI, et cetera, are probably already doing, but it's increasingly hard to get that signal out of them. So if we look at this, like reasoning is really also unlocking really new language model applications. I think this is the same search query, which is like, as an RL researcher, I need to find this all the time. I forget that it's called coast runners, and then you Google like over optimization 20 times to find it. But I tried asking O3 and it like literally gave me the download link directly, so I didn't even have to do anything. And that's a very unusual use case to just pop out of this reasoning training where math and code was the real thing to start with. And O3 is great. It's the model that I use the most for finding information. And this just really is the signal that I have that a lot of new interesting things are coming down the pipe. I would say it's starting to unlock a lot of new language model applications that I use some of these. So this is a screenshot of deep research. It's great. You can use it in really creative ways, like prompt it to look at your website and find typos, or look at only the material on your website and things like this. It's actually more steerable than you may expect. Claude Code, which I describe as just the vibes are very good. It's fun. I'm not a serious software engineer, so I don't use it on hard things, but I use it for fun things because I can put the company API key in and just kind of mess around, like helping me build the website for this book that I wrote online. And then there's the really serious things, which are like codecs and these fully autonomous agents that are starting to come. If you play with it, it's obvious that the form factor is going to be able to work. I'm sure there are people that are getting a lot of value out of it right now. I think for ML tasks, it's like there's no GPUs in it right now. And if you are dealing with open models, it's like they just added internet. So like it wasn't going to be able to go back and forth and look at like Hugging Face configs or something and all these headaches that you don't want to deal with. But in the 6 months, like all of these things are going to be stuff you should be using on a day-to-day basis. And this is all downstream of this kind of step change in performance from reasoning models. And then this is kind of like another plot that's been talked about. And when I look at this, it's like through 2024, if we look at like GPT-4o, things really were saturating then. And then there's these new Sonnet models in 01, which really helped push out the frontier in time horizon. So this is the y-axis is how long a task can roughly be completed by the models in time, which is kind of a weird way to measure it because things will get faster. But it's going to keep going, and this reasoning model is the technique that was kind of unlocked in order to figure out how to push the limits. And when you look at things like this, it's not that just we're like on a path determined from AI and more gains are going to come. It's really like we have to think about what the models need to be able to do in order to keep pushing out these frontiers. So there's a lot of human effort that goes into continuing the trends of AI progress. So it's like gains aren't free, and I'm thinking that a lot of planning and kind of thinking about training in a bit of a different way beyond just reasoning skills is going to be what helps push this and enable these language modeling applications and products that are kind of in their early stages to really shine. So this is a core question that I'm thinking about is like, what do I have to do to come up with a research plan to train reasoning models that can work autonomously and really have meaningful ideas for what planning would be? So I kind of came up with a taxonomy that has a few different what I call traits within it. The first one is skills, which we've pretty much already done. Skills are like getting really good at math and code. Inference time scaling was useful to getting there, but they kind of become more researchy over time. I think for products, calibration is going to be crucial, which is like these models overthink like crazy. So they need to be able to kind of have some calibration to how many output tokens are used relative to the difficulty of the problem. And this will kind of become more important when we're spending more on each task that we're planning. And then the last two are subsets of planning that I'm thinking about, and happy to take feedback on this taxonomy, but like strategy, which is just going in the right direction and knowing different things that you can try. Because it's really hard for these language models to really change course, where they can backtrack a little bit, but restarting their plan is hard. And then as tasks become very hard, we need to do abstraction, which is like the model has to choose on its own how to break down a problem into different things that it can do on its own. I think right now humans would often do this, but if we want language models to do very hard things, they have to make a plan that has subtasks that are actually tractable, or it calls in a bigger model to do that for it. But these are things that the models aren't going to do natively. Natively, they're trying to like doing math problem solving. Like that doesn't have clear abstraction on like this task I can do and with this additional tool and all these things. So this is a new thing that we're going to have to add. So to kind of summarize, it's like we have skills, we have research or calibration, and I'll highlight some of it. But like planning is a new frontier where people are talking about it, and we really need to think about like how we will actually put this into the models. So to just put this up on the slide, what we call reinforcement learning with verifiable rewards looks very simple. I think a lot of RL and language models, especially before you get into this multi-turn setting, has been you take prompts, the agent creates a completion to the prompt, and then you score the completions. And with those scored completions, you can update the weights to the model. It's been single turn, it's been very simple. I'll have to update this diagram for multi-turn and tools, and it makes it a little bit more complex. But the core of it is just a language model generates completions and gets feedback on it. And it's good to just take time to look at these skills. These are a collection of evals, and we can look at like where GPT-4o was, and these were the hardest evals that have existed and were called like the frontier of AI. And if we look at the O1 improvements and the like O3 improvements in quick succession, these are really incredible eval gains that are mostly just from adding this new type of training in. And the core of this argument is that we need to do something similar if we want planning to work. So I would say that a lot of the planning tasks look mostly like Humanities Last Exam and Amy, just after adding this reasoning skill, and we need to figure out what other types of things these models are going to be able to do. So it's like this list of reasoning abilities, that these kind of like low-level skills, is going to continue to go up. I think the most recent one, if you look at recent DeepSeek models or recent Quen models, is really this tool use being added in, and that's going to build more models like O3. So using O3 just feels very different because it is this kind of combination of tool use with reasoning, and it's obviously good at math and code. But I think these kind of low-level skills that we expect from reasoning training, we're going to keep getting more of them as we figure out what is useful. I think an abstraction for the kind of agenticness on top of tool use is going to be very nice, but it's hard to measure. And people mostly say that Claude is the best at that, but it's not yet super established on how we measure it or communicate it across different models. And then this is where we get into the fun, interesting things. I think it's hard for us because calibration is passed to the user, which is we have all sorts of things like model selectors if you're a ChatGPT user. Claude has reasoning on-off with this extended thinking, and Gemini has something similar, and there's these reasoning effort selectors in the API. And this is really rough on a user side of things, and making it so the model knows this will just really make it so it's easier to find the right model for the job, and just kind of, your kind of spent tokens for no reason will go down a lot. It's kind of obvious to want it, and then it becomes a bigger problem the longer we don't have this. Some examples from when overthinking was kind of identified as a problem. It's like the left half of this is you can ask a language model like what is 2 + 3, and you can see these reasoning models use hundreds to 1,000 tokens or something that could realistically be like 1 token as an output. And then on the right is a kind of comparison of sequence lengths from a standard like non-RLL trained instruction model versus the QWQ thinking model. And you really can gain this like 10 to 100x in token spend when you shift to a reasoning model. And if you do that in a way that is wasteful, it's just gonna really load your infrastructure and cost. And as a user, I don't wanna wait minutes for an easy question, and I don't wanna have to switch models or providers to deal with that. So I think one of the things that once we start to have this calibration is this kind of strategy idea. And on the right, I went to the, I think it's Epoch AI website. I took a question, one of their example questions from Frontier Math. And I was like, does this new DeepSeek R1 0528 model, like, does it do any semblance of planning when it starts? And you ask it a math problem, it's just like, okay, the first thing I'm gonna do is I need to construct a polynomial. It's like, it just goes right in, and it doesn't do anything like trying to sketch the problem before it thinks. And this is gonna probably output 10 to 40,000 tokens, and if it's gonna need to do another 10x there, it's just like, if that's all in the wrong direction, that's multiple dollars of spend and a lot of latency that's just totally useless. And most of these applications are set up to expect a latency between 1 and 30 minutes. So it's like, there is just a timeout they are fighting. So either going in the wrong direction or just thinking way too hard about a sub-problem is just gonna make it so the user leaves. So right now, these models, I said, they do very little planning on their own. But as we look at these applications, they're very likely prompted to plan, which is like the beginning of deep research and Claude Code. And we kind of have to make it so that is model native rather than something that we do manually. And then once we look at this plan, there's all these implementation details across something like deep research or Codex, which is like, how do I manage the memory? So we have Claude Code compresses its memory when it fills up its context window. We don't know if that's the optimal way for every application. We want to avoid repeating the same mistakes. We talked, Greg was talking about the playing Pokemon earlier, which is a great example of that. We want to have tractable parts. We want to offload thinking if we have a really challenging part. So I'll talk about parallel compute a little bit later as a way to kind of boost through harder things. And really we want language models to call multiple other models in parallel. So right now people are spinning up tmux and launching Claude Code in 10 windows to do this themselves, but there's no reason a language model can't be able to do that. It just needs to know the right way to approach it. And as I've started with this idea of kind of we need effort or like we need to make effort to add new capabilities into language models. When I think about this kind of story of QStar that became Strawberry, that became O1, the reason that it was in the news for so long and was such a big deal is like, it was a major effort for OpenAI, spending like 12 to 18 months building these initial reasoning traces that they could then train an initial model on that has some of these behaviors. So it took a lot of human data to get things like backtracking and verification to be reliable in their models. And we need to go through a similar arc with planning, but with planning, the kind of outputs that we're gonna train on are much more intuitive than something like reasoning. I think if I were to ask you to sit down and write a 10,000 token reasoning trace with backtracking, it's like you can't really do this, but a lot of expert people can write a 5 to 10 step plan that is very good, or check the work of Gemini or OpenAI when asked to write an initial plan. So I'm a lot more optimistic on being able to hill climb on this. And then it goes through the same path where once you have initial data, you can do some SFT, and then the hard question is if the RL and even bigger tasks can reinforce these planning styles. On the right, I added kind of a hypothetical, which is like we already have thinking tokens before answer tokens, and there's no reason we can't apply more structure to our models to just really make them plan out their answer before they think. So to give a bit more depth on this idea of skill versus planning, if we go back to this example, I would say that O3 is extremely skilled at search. So being able to find a piece of niche information that researchers in a field know of but can't quite remember the exact search words, that is an incredible skill. But when you try to put this into something like deep research, there's this lack of planning is making it so that sometimes you get a masterpiece and sometimes you get a dud. And as these models get better at planning, it'll just be more thorough and reliable in getting the kind of coverage that you want. So it's like, it's crazy that we have models that can do this search, but if you ask it to recommend some sort of electronics purchase or something, it's really hard to trust because it can't just know how to pull in the right information and how hard it should try to do all that coverage. So to kind of summarize, these are the 4 things that I presented. I think you can obviously add more to these. You could call a mix of strategy and abstraction. There's like, you could call what I was describing as like context management in many ways. But really you just want to have things like this so that you can break down the training problem and think about data acquisition or new algorithmic methods for kind of each of these tasks. And I mentioned parallel compute because I think this is an interesting one, because if you use O1 Pro, it's still been one of the best models and the most robust models for quite some time, and I've been very excited for O3 Pro. But it doesn't solve problems in the same way as like traditional inference time scaling, where inference time scaling just made a bunch of things that didn't work go from 0 to 1. Where this parallel compute is really like, it makes things more robust. It just makes them nicer. And it seems like this kind of RL training is something that can encourage exploration. And then if you apply more compute in parallel, it feels something kind of exploiting and getting a really well-crafted answer. So there's a time when you want that, but it doesn't solve every problem. And to kind of transition into the end of this talk, it's like, there's been a lot of talks today saying the things that you can do with RL. And there's obviously a lot of talk on the ground of what is called continual learning. And if we're just continually using very long horizon RL tasks to update a model and diminish the need of pre-training. And there are a lot of data points that were closer to that in many ways. I think continual learning has a big algorithmic bottleneck, but just like scaling up RL further is very tractable and something that is happening. So if people are to ask me what I'm working on at AI2 and what I'm thinking about, this is my like rough summary of what I think our research plan looks like to train a reasoning model without all the in-between the line details. So step 1 is you just get a lot of questions that have verified answers across a wide variety of domains. Most of these will be math and code because that's what is out there. And then 2, if you look at all these recipe papers, they're having a step where they filter the questions based on the difficulty with respect to your base model. So if a question is solved 0 out of 100 times by your base model, or 100 out of 100, you don't want questions that look like that, because you're both not only wasting compute, but you're messing up the gradients in your RL updates to make them a bit noisier. And once you do that, you just want to make a stable RL run that'll go through all these questions and have the numbers keep going up. And that's the core of it, is really stable infrastructure and data. And then you can tap into all these research papers that tell you to do methods like overlong filtering or different clipping or resetting the reference model. And that'll give you a few percentage points on the top, where really it's just data and stable infrastructure. And this kind of leads to the provocation, which is like, what if we rename post-training as training? And if OpenAI 01 was like 1% of compute is post-training relative to pre-training, they've already said that 03 has increased it by 10x. So if the numbers started at 1%, you're very quickly getting to what you may see as like parity in compute in terms of GPU hours between pre-training and post-training, which if you were to take anybody back a year ago before 01 would seem pretty unfathomable. And one of the fun data points for this is that the DeepSeek v3 paper, and you kind of watch DeepSeek's transition into becoming more serious about post-training. Like the original DeepSeek v3 paper, they used 0.18% of compute on post-training in GPU hours. And they said their pre-training takes about 2 months, and there was a deleted tweet from one of their RL researchers that said the R1 training took a few weeks. So if you make a few very strong, probably not completely accurate assumptions that RL was on the whole cluster, that would already be 10 to 20% of their compute. I think like specific things for DeepSeek are like, oh, their pre-training efficiency is probably way better than their RL code and things like this. But scaling RL is a very real thing. If you look at this, if you look at frontier labs, and you look at the types of tasks that people want to solve with these long-term plans. So it's good to kind of embrace what you think these models will be able to do and kind of break down tasks on their own and solve some of them. So thanks for having me, and let me know what you think.
All right, so for our final talk of the track for the day, we have the great pleasure of hearing from Chris Szegedy. So Chris was a researcher at Google for a long time, became the co-founder of XAI, where he was for a couple of years, and is now working on a new startup. He's going to be talking to us today about the path towards verified superintelligence, which I'm very curious about myself. Unfortunately, Chris did have a last-minute conflict, so he's not able to be here in person. He will be here on Zoom. So we should see in just a moment him coming up and be able to see him talk. So let's welcome Chris. I see people in the AV corner just looking very, okay, we're good. I feel like we've all been here with Zoom before, so we'll give Chris a moment.
Sorry, I was just, I had to grant some permission to Zoom. Somehow it didn't have a permission to share my window, and I needed to check out.
We can all empathize. I think this has happened to everyone on some meeting.
Yeah, okay, now I get it. Okay, cool. So can you see my presentation slide?
Yes, we can see it.
Yeah, okay, cool. So sorry about the delay. So I'm Christian Szegedy, and I just joined Morflex as a chief scientist. So I will tell a bit about why, why I believe in what we are doing, and why I think that technology is really will allow us to take to the next level. But first, let me give some overview on how I view the progress of AI in the past So basically, when I started doing deep learning, that was around 2011, and classification was still a big question mark. So nobody really knew whether deep learning will ever take on or not, so nobody really worked on it. It was like Google Brain was like 4 people. So when AlexNet came out, so here maybe I just put up a few examples of what I believe in these trends were, how they, what is a good example of those trends. Then structured prediction became a big research topic. So object detection was a large part of it, so that people got really excited because it was an important application domain. So then we learned like around 2015 that yeah, we can do object detection, we can do almost any structured output can be output by neural networks. Then RL became a big, so the big trend of the where most people were most excited about, rightly so. So it was AlphaZero is probably the most important landmark in that domain, but also Dota by OpenAI. But in the meantime, also transformers came out, and then unsupervised retraining started to become the biggest driving force of research in AI. So it's a special case of structured prediction in some sense, but still it was taken to the next level by just scaling up compute and data to almost insane amounts, like training on almost all of the internet accessible data. And that's where we are roughly. And thinking models came out like 2 years ago. They are relatively new. And then I think the big idea behind them is that you have to create this side information. That is the chain of thought. And that is basically the learning from supervised RL that reinforcement learning on large language models is really hard, but if you're reinforcing the chain of thought, or the reasoning chain, then you can suddenly make it work. It was still a lot of work to make it. So kickstart the whole process, so it was not obvious, but the start paper was a prototype on showing that yeah, this can be kickstarted, and then based on that idea, almost all of the current reasoning models work. So basically the lessons that we could draw from all these trends is the first lesson was in the first epoch is that deep learning works at all. Then deep learning can create artifacts. Then the AlphaZero. Supervised reinforcement learning was that chain of thought also matters, so you can scale up inference time essentially. Now the question is, what is the next big trend that we can expect to happen? And that's what I would like to talk about. But in order to guess it, let's see what were the limitations of each of these trends. So first we had you need to have label data. So basically we needed a lot of human labelers to label certain data points. Then structured prediction took that effort into the next level because marking objects is harder than just labeling the pictures. Then deep RL, it was a huge success. are the bottlenecks to AI self-improvement? So I mean, it's the human-generated labels, the human-generated data, and now we have the human-generated tasks and human supervision, and even human-generated verifiable problems. So in order to scale up reinforcement learning, you need to generate a lot of environments. So basically what we can say is that the bottleneck to AI self-improvement is basically human. Everything, every aspect of the learning process that relies on human input is prone to be problematic. It adds either it adds friction or there is a limited source of data because human data is getting less and less available that we haven't trained on. So what we really have to figure out how we create open-ended self-improvement. So that is a hard question, as the previous talk, but Marten was also pointing this out, that that's something is the future, but the real question is how do we really scale up RL so that it will become, so basically a combination of large language model, structured prediction, and really superhuman reasoning in almost every aspect. So how do we get to that? So what is the way to reach self-improvement? So we basically have to remove these bottlenecks. We don't want to, now that we ran out of all this human-generated data from the internet, now the question is, now we are running into the problem of having only a very limited set of human-generated environments that we can train on. We already ran out of them. So people hire a lot of people, and it takes a lot of money and effort to create this environment and create tasks for the AI that can actually learn. So, in short, we can say that the AI needs compute, it wants agency, it needs challenges, and it needs feedback, basically a verification signal that gives a reward to the agent. So these are the most important part of making open-ended self-improvement work. So from these basic principles, we can make some claims on how we can solve these bottlenecks. So one, I think, is the first bottleneck that almost everybody is concerned nowadays is having good environments in which the AI can run safely. So it doesn't have to be, so we don't want the AI to just go into some environment and get full agency and then corrupt your computer or corrupt your cloud environment, etc. So there is a tension between agency and safety. Because if the AI is very, get full agency, then it can be dangerous or it can break itself. So it can basically, we want an environment in which the agent can have absolutely fluid, so it can have root access or even web access, and we also want the agent to be able to backtrack its decisions, even if it installed the wrong package, for example, for a task, or it created the wrong program, or it deleted an important tool from the tool chain. So in this case, the agent should be able to decide, okay, I want to go back and I want to try a different path. So this is not just important for inference time when we execute the agent, it's even more important for reinforcement learning, where you are running the agent on a lot of problems. So basically, getting a sandboxing environment that allows you to do a lot of branchings and undos, basically like a version control system for snapshots, is an absolute must for a sophisticated agent, in my opinion. So the other important bottleneck that we have seen is the lack of good verifiable problems. So what I think the next generation of AI will need to be able to create its own curriculum of problems. So you don't want the agent to be given a set of problems to train on. We should just give them high-level task of learn to be a good Rust programmer, for example. And then it should go to the internet and find all the important, so improve its own skills without having a set curriculum. So, and we want the agent to have this ongoing continuous learning, as Nathan also mentioned. I think that's very important, and that's the future of AI, that is being able to do the learning while it's actually executing useful tasks as well. So I think that will be very important in the next few years. But most importantly, and that's why I put such a emphasis on verification and verified AI, is that we need very strong verifiers and validators. So what do I mean by that? So verifier is an agent that verifies the correctness of a solution, but validator is also, it could be the same agent. It validates that the problem formulation was interpreted correctly, so that the human input was correctly interpreted. So the first one actually could be done with also external verifier. You don't even need models for that. It can be an agent that just uses some kind of verifier that, for example, runs a code or calls a proof checker, so doing some formal verification, etc. But validator should be model-based, because that checks the alignment between the human and the machine. And that's very important. So, and then we think that the next generation of AI will be able to produce safe and independently verifiable artifacts. So we want code that actually comes with its own guarantees of correctness. And that's very important. So today, computer chips already always verified extensively, and we don't do that with software. But I think in the next 5 years, the AI-driven cyber attacks will be so severe that nobody will ever try to run any software that is not fully formally verified, at least for some purposes. So, and while the AI produces verifiable artifacts, so basically it shouldn't just produce code, it should produce code and proof of correctness of that code as well. And at the same time, it will have to improve its own alignment. So it should get better and better at respecting and guessing the human's intent as well. So that's what basically I believe is this self-supervised reinforcement learning, or what I call is verified superintelligence. And they sound different, but actually they are the same things. I think this is possible. So we can get to self-supervised reinforcement learning, which will be such a big leap as from supervised learning, just like training on label data, to going to training on the whole internet. So this will be, in my opinion, the next big step. It's an agent that can create its own problems. It acts as its own verifier, and it will bootstrap itself from all of internet or whatever part of internet you want. But it will be autonomously finding its own problems. It creates its own problems and solves them. So we don't really need to give it any more problems. So basically, how do we get to this infinite supply of problems? So that's the hard question. And what we think is the key to that is verification. So we need, what I'm suggesting is that we mine the internet for actual problems, but turn them into formally verifiable artifacts. And formally verified meaning that the correctness of the artifacts can be checked. So for example, code or mathematical problems, you can use a theorem prover, for example, to check the logical correctness of things, which is definitely hard, but not impossible. It's getting more and more possible. And at the same time, it uses these signals to create rewards for alignment. So when, for example, an artifact, it gets from the internet, for example, code this or that problem, and then it tries to code it up and read some solution, it can say, okay, does this solution really aligns with what was meant here? And I think this can be bootstrapped with various reward signals coming from cycle consistency ideas. So these can be, in my opinion, also trained and enforced. So correctness and alignment has this interplay between them. So because if the output is not correct, then it cannot be properly aligned. So, and what I really believe is that we can do most of the correctness checking model free, so that it doesn't require necessarily a model that that checks the output. It's more like a well-defined verifiable artifact, like in a NP problem, that you have also always a verifier. Alignment must be model-based, unfortunately. But I think the interplay between the two allows us to improve on both fronts. And I think verification should be always agentic. So we want to move away from having like a model trained to verify something. The verifier also should have tool access and being able to go into an environment where the artifact was produced, for example, a software system, and then test that software system in all kinds of scenarios, for example. So basically, this is a very rough sketch of how I believe this roadmap to work out is that we have like a generator agent and a validator, a verifier agent. The agents can share the same model, but they all connected to something like the Morph cloud that we are working on. This cloud allows you to branch a lot of sandboxes, try various versions, roll back, etc. And then the generator provides solutions to the verifier, and the verifier and validator give back reward signals to train the generator. So, and they both give each other basically kind of reward signals. And the potential tasks are taken from the web, and they also should be agentically generated or crawled by the agent itself, not by some human that selects them or creates them. So they should be automatically created. And then the important part is that we want the agent to be able to produce artifacts that are verified completely independently. So you don't want to trust the AI, you want to verify it. So these are the main properties that I really want, is that we have first-class verification in this system. We have first-class alignment in this system. So these are grounding principles of how to build a system, and they should be from the ground up provided. So they should be goals of the agent that we are reinforcing the whole time. And we want to get model-free verifiable artifacts so that we can trust the AI without any AI intervention. These proofs might be created by a lot of AI computations, but they should be just verifiable. And then this will give us infinite supply of hard problems. So what are the application domains of this verified superintelligence? So I think it will be mandatory for AI software engineers. So if you make one bug in 100 lines of code, that's today okay, roughly. It's still, you get some value out of your model. But if you want to create like agency that the model can work for hours on a complicated software project completely autonomously, then one bug every 100 lines is impossible. Then you will never get anything done. So therefore, I think we need to have ongoing verification all the time in the process. Another important problem is cybersecurity. We want our systems to be hacking proof. So we don't want external AIs to hack in our systems, which will be more and more happening in the next few years. Also, engineering. So engineering requires a lot of mathematics and reasoning, and sciences, of course, also will require this. So we believe that mathematics will also be properly verified in the next few years, mostly by AI agents. So the goal here is that verified superintelligence, we want a trustlessly aligned AI. This means that we don't just want to trust the AI, we want to actually check it. And this check should be possible. So that's, okay, sorry. Yeah. So that concludes my talk. So I'm just, stop share, yeah. So I'm happy to take questions.
Thank you so much, Chris. We appreciate you taking the time. All right, well, this concludes our track. This concludes the breakout sessions for today. Yes. I think, I don't think we'll be able to do questions because we are a little bit over time, unfortunately. At 5 o'clock, it's at 4 o'clock. Yes, at 4 o'clock, there's going to be keynotes on the main stage. So look forward to seeing all of you there and hope you have a good rest of your conference.